In this segment, I want to talk a little bit about buoyancy. Buoyancy is a force it's important in all different aspects of our lives, but especially when we start thinking about floating and liquids and objects in liquids. So, I have here a piece of wood, and just a block of wood. It's oak, ordinary wood. And if I put it in here, you probably won't be terribly surprised to see that it floats. Okay, so I've got my wood in there, and it definitely does float. Well, let's think about the forces on this block of wood right now. Is it accelerating? No, hopefully you agree that this block of wood is not accelerating. Therefore, the force on this block of wood, the net force, or the total force, I should say, is zero. The total force on this block of wood is zero because it's not accelerating. We could say it's in static equilibrium. Well, okay, we know that weight is pulling down. So is there some other force that's pushing up? Well, there must be. There absolutely must be. It's not accelerating, remember? So we must have some force pushing upward on the block of wood. What is that force? I don't know, we could call it the floaty force. That would work. In this class, we're going to call it the buoyant force. And it's the buoyant force that pushes up on that object. And the buoyant force is a force that exists anytime you have an object that's immersed in a fluid. Really, there's a buoyant force on me right now because I'm immersed in air. Now that's small, and maybe we'll revisit that idea later. It most often shows up when we're talking about liquids, but there's a buoyant force in objects in air also. This is how a hot air balloon can float. Right? A hot air balloon certainly has weight pulling down on it. What force pushes up on it in order to keep it aloft? It is the buoyant force. That's what we're going to learn about in this segment. So, what about this? Here's a rock, and it's about the same size as that piece of wood, ballpark the same size. And what if I put it in here? Well, again, I don't think anyone's going to be real surprised by the result. Okay, did my rock float? No. Again, not surprising. Is there a buoyant force on the rock? It's not floating. It turns out there is. There is a buoyant force on the rock. There's a buoyant force on any object that's immersed in a fluid. Here I have a piece of styrofoam. This piece of styrofoam is about the same size as my piece of wood also. And notice if I put it in the water, it floats very high in the water, right? Notice my piece of oak is floating with just barely the top of it above the surface of water, whereas my piece of styrofoam is floating with most of it out of the water. Well, this relates very closely to the first idea we introduced in chapter 13, which is that of density, right? And so the foam, of course, is much less dense than the oak, and so it sits much higher in the water. All three of these objects have a buoyant force on them. The buoyant force on each of these objects is slightly different, however. But because each of them are immersed or partially immersed in a fluid, they are each experiencing a buoyant force. Let's look at it a little bit more closely. If you look at the PowerPoint, you see I have a picture here. And this picture shows an object immersed in some liquid. Now, recall that the pressure inside a liquid increases with depth. The pressure lower in the liquid is greater than the pressure at the top of the liquid. So, looking at this object that's immersed in this fluid, the pressure in the fluid gives rise to a force. We learned in a previous segment that the force that pressure creates is always perpendicular to any surface. Remember, pressure is not a vector, but the force that pressure creates is a vector. So pressure creates a force which is perpendicular to any surface. So we've got this force pushing down on the top and a force pushing up on the bottom, which is greater. Well, the force pushing up on the bottom is greater than the force pushing down on the top. Why? Because the pressure increases with depth. Since the pressure is greater at the bottom of the object than it is at the top, a greater force is applied at the bottom than there is at the top. This yields a net force upward, which is the buoyant force. Now, let's be clear here. There's also a weight, which is not included here. So, what we're saying here is that F up minus F down is a number. It's a positive number, and that is the buoyant force. Now, we know that pressure creates a force which is also pushing on the sides, but those all cancel, right? The reason we get the buoyant force is because the pressure is greater on the bottom than it is on the top. This yields the buoyant force. In order to do an analysis of this subject and put some numbers on it, we need a new idea, and that is Archimedes' principle. So Archimedes lived around 250 BC on the island of Syracuse, which was a Greek nation-state at the time. And he was a brilliant thinker. He was probably the most brilliant thinker of his day. He came very close to inventing calculus. In fact, he predated the invention of symbolic algebra by 1,000 years. But I suspect if he had had the invention of symbolic algebra to use, he would have invented calculus. He had all of the big ideas of calculus. He just didn't have the tools to bring it into practice. That is symbolic algebra. That had to wait for Newton to put all those pieces together. Okay, so he lived on this island. He was a brilliant thinker, and he in service to his king, he came up with many new inventions. He invented a lot of devices for warfare. They were a very successful nation state. There's a possibly apocryphal story about Archimedes and how he came up with this idea. And that is that somebody gave the king of Syracuse a crown. And the king was suspicious, though. It appeared to be gold, but the king was very suspicious. And he said, I don't know if this is pure gold or not. I suspect I have been duped. And so he came to Archimedes and he said, Archimedes, I want you to figure out if this crown is made of pure gold, but I don't want to just cut it open or something, because then I will have ruined it. If it truly is made of pure gold, then I will have ruined a beautiful creation. But if it isn't, then I want to know, so that the person who has tricked me can be punished. So the story goes. And so the story goes that Archimedes, one evening, was lowering his bulk into the bathtub. And as he lowered his bulk into the bathtub, he saw the water level rise around him. As he lowered, and the lower he got, the higher the water level rose. And he had this idea in a flash of inspiration. And he jumped out of his tub, and he ran through the castle naked, yelling, Eureka! Eureka! I have figured it out! Well, it might be true, or it might not be. And supposedly the crown was not made of gold, and off with his head. I don't know. The mathematics in it isn't quite that exciting. But it's an interesting story, I suppose. So what is Archimedes' principle then? What is this thing that Archimedes figured out in 250 BC? The thing that he figured out was that a fluid will always exert an upward buoyant force on an object, immersed in the fluid. Always. So any object that is immersed or partially immersed in a fluid experiences an upward buoyant force. The magnitude of the buoyant force is equal to the weight of the displaced fluid. That last bit takes a little bit to wrap our brains around, right? It's words we've seen before, but I think we need to wrap our brains around exactly what that means. And in order to get there, let's imagine a situation. We're going to do a thought experiment, right? Here is just a bucket of water. There's nothing in it. What we're going to do is we're going to imagine a chunk of this water. And as we learned last semester, whether we're thinking about what we call the object of interest is completely up to us, right? We can group objects together and collectively deal with them as the object of interest, or we can separate them out, right? Instead of dealing with each water molecule here as our object of interest, we're going to arbitrarily pick some weird kidney-shaped sort of package of water, and we're going to say that's our object of interest. So we've drawn an imaginary boundary around our object of interest. Is that object of interest accelerating? No, it is not. It's just a chunk in the middle of this water. It's neither going up nor down. It is in equilibrium. Well, then what is the net force on that object? It must be zero, right? The net force on that must be zero because it's not accelerating. Well, that means it certainly has weight. It certainly has weight pulling down. That means there must be some upward force that is balancing it out. What is that force? Well, as we've learned, it is the buoyant force. So the buoyant force in this situation must be equal to the weight. Well, shoot. It must be equal to the weight of the water, because it is the water, right? And so if we were to replace that imaginary boundary with a real object, we'd see that the buoyant force did not change. The buoyant force is exactly the same. The buoyant force is caused not by the object itself, but rather by the water that the object is displacing. And so this gives rise to the idea that the buoyant force is equal to the weight of the displaced fluid. It clearly is here, because the object isn't accelerating. Here, it turns out it's the exact same, right? So replacing the actual water with a different object that is not water yields the exact same upward buoyant force. Now, recall that the weight of any object is just mg. And so we could always write W equals mg, right? We could write that anytime we wanted. Now, in this case, we're talking about the weight of the displaced fluid. Again, referring to Archimedes' principle. Archimedes' principle says the buoyant force is equal to the weight of the displaced fluid. I can write the weight of the displaced fluid as the mass of the fluid times gravity. Now, as we learned in a previous segment, we can write mass as density times volume. So this is the density of the fluid times the volume of the fluid times gravity. Well, that's just the weight of the displaced fluid, isn't it? But Archimedes' principle tells us that this is equal to the buoyant force. And so we end up with the conclusion that the buoyant force is equal to the density of the fluid times the volume of the fluid times g. That's Archimedes' principle. It's a fairly easy idea. In practice, it can be a little bit tricky to apply. Let's bring our three objects back in. Let's compare my styrofoam and my block of wood. Apparently, according to Archimedes' principle, the buoyant upward force is equal to the weight of the displaced water. What do I mean by that? Notice the piece of wood, right? The piece of wood is sitting quite low in the water. And so it is displacing more fluid than the styrofoam is. This term, displaced fluid, means it's how much water isn't there because instead there's the object, right? If you look at this block of wood, right, the part that is under the surface of the water, there's no water there, there's wood. That's not like some crazy idea. It's wood, not water, right? So how much fluid did I displace? Well, it's equal to the volume of wood that's underwater, because instead of water, there's wood, right? Same thing for the styrofoam, only here there's much less water displaced, right? So upon which of these is the buoyant force greater? The wood or the styrofoam? The buoyant force is greater on the wood because the wood is displacing more fluid. They're both floating, so the weight of the fluid displaced is equal to the weight of the object. The wood is heavier than the styrofoam is. Since they were both floating, the buoyant force on the wood must have been greater. We can see that also because the wood displaced more water. Again, our rock, when I put it in there, it also has a buoyant force on it. How much? Well, it's equal to the weight of the water that isn't right there because instead the rock is right there. Okay, so that's what we mean by displaced fluid. As I previously mentioned, when an object floats, it means that the upward buoyant force is exactly equal to the downward weight force pulling on the object. Doing a little algebra yields this equation right here, that the volume of the fluid displaced is equal to the density of the object divided by the density of the fluid times the volume of the object. Again, this volume of the fluid displaced, we can interpret that as being the volume of this block that is under the water. In other words, it's the volume where there is the block instead of water. And so this is interesting, right? We can reach all kinds of interesting conclusions from this. In particular, the density of ice is about 90% that of water. Therefore, when an iceberg floats, an ice cube or an iceberg, the displaced water is 90% of the volume of ice. That means that 90% of the ice is below water and 10% is above. So, the proverbial tip of the iceberg is 10% of the iceberg. Okay, let's do a couple of examples. Here's one. Two blocks of identical size are submerged in water. One is made of lead, and of course lead is heavy, it's a very dense object, and the other is aluminum, which is much lighter. But they both sink, right? So we've got same size, but since lead is more dense, the lead block is heavier. And they both sink, so they are both resting on the bottom. Why don't you pause the video and ponder it? I'll see you on the other side. Okay, well, I've drawn a little picture here. I've got my lead block and my aluminum block, and they're both resting on the bottom of my container because they both sink. They are the same size. Well, Archimedes' principle tells us that the buoyant force is equal to the weight of the displaced fluid. How does the fluid displaced by the lead block compare to the fluid displaced by the aluminum block? Well, they're the same size. And so they're displacing the exact same amount of water. So the buoyant forces must be equal. How about this one? Two blocks are identical size. One is made of lead, it sits on the bottom of the pond, and the other is made of wood, and it floats on top. Upon which is the buoyant force greater? The lead, the wood, or are they the same again? Why don't you ponder it? It might help to draw a picture. I'll see you on the other side. Okay, well, here's my drawing. Two blocks, they are the same size. My lead sinks. How much water is the lead displacing? Well, everywhere where there is a lead block, there is not water, right? So the lead block is displacing fluid equal to its entire volume. However, the wood block, notice it is not displacing an amount of water equal to its own volume because it is floating. And so the water displaced by the wood block is simply this part that's underwater. Which block is displacing more fluid? The lead block is. Therefore, upon which is the buoyant force greater? On the lead block. Now, many students look at this and they say, yeah, but this one's floating. Doesn't it require more force to make it float? Well, don't forget that it's also much less dense, and it has a smaller mass. And so it has a smaller weight. And so it requires less of a buoyant force in order to make it float. How about this one? This one's kind of a tricky one. A barge filled with ore floats in a canal lock. We better pause for a minute. What's a canal lock? If you've never seen a lock, it is a way for boats to go upstream and downstream across, say rapids or something. It's an engineering project, and basically what it is it's an enclosed container of water. And so, say a boat had to go up over a waterfall. The waterfall's over here, and then over here we've got this engineering project called the canal lock. And the boat would go into the lock, the gates are closed, and then water is pumped into the lock, the boat raises up until it's at the level of the top of the waterfall. Now we open up the gates on the upstream side, and the boat can leave. Okay, so for the purposes of this question, a lock is simply an enclosed vessel of water. This right here is a perfectly decent model for a lock. Okay, so we've got a barge and it's filled with ore in a canal lock. We toss the ore overboard. What happens to the water level in the lock? Will it rise, fall, or remain the same? Why don't you go ahead and think about this one a little bit. I'll see you on the other side. All right, so this one is a little bit challenging to draw a nice picture of. So instead, I've got myself a lock here, and I've added some red food coloring to the water so that you can see the water level just a little bit better. And then what I also have here is a boat. This is my barge, a little tinfoil barge, and some rocks. I got several rocks in there. This is my oar. Okay, so here's my boat with my oar, and we'll go ahead and get my barge floating here. Okay, there we go. I have my barge floating in the lock. All right, now that I've got my barge floating, let's go ahead and we're going to use this piece of tape here to just mark where the water level is. Okay, there we go. The bottom of the tape is level with the top of the water. My barge is floating. Let's go ahead and empty the ore out. Okay, so here we go. I'm going to empty my ore, dump it into the lock. There we go. My ore is now in the lock, and my boat is floating. What happened to the water level? Well, hopefully you can see that the water level went down, didn't it? All right, that's kind of a tricky one. That usually surprises students. And the way to think about it is, what's more dense, my ore or my water? Well, definitely the ore, right? And so when the ore is floating inside my aluminum boat, then we know that the upward force, the buoyant force on the ore is absolutely equal to the weight of the ore. If we can neglect the weight of my tinfoil. It's very small. So the downward weight of the ore is balanced by the upward buoyant force when it is floating. Okay, that means that the water displaced has a volume such that the mass, or the weight of that water displaced, is equal to the weight of my ore. Now, when I throw the ore overboard and it's sitting in the bottom of the lock, it's no longer floating. And so the buoyant force is not necessarily equal to its weight. In fact, it isn't. In fact, the weight is greater than the buoyant force, which is why the rocks accelerated to the bottom of the pond when I first dropped them in there. So the rocks are sitting on the bottom of the pond because when they're at rest on the bottom of the pond, the buoyant force is less than their weight. Therefore, the buoyant force is less on the rocks when they are out of the boat than it is when they are in. Therefore, they displace less water out than they do in, which is why the water level fell. Let's do a numerical example using the buoyant force. A ball weighing 1 Newton has a density 1/3 that of water. What is the tension in the string when the ball is held underwater as shown? Okay, so we've got this problem, and it's asking us about tension. It's immersed in a fluid, so it's definitely a buoyant force type of a problem. Now, buoyant force problems are force problems fundamentally, right? Really, the buoyant force, it's kind of nice because we're not learning a new problem-solving strategy here. We're just learning about a new kind of force. But we've spent a lot of time learning how to solve force problems. And so we're just going to do those steps. First, we're going to draw a quick picture. Okay, next we should draw a free body diagram for the object of interest. Well, what is our object of interest? The water is not a good choice. The string is not a good choice. We've never really made the string our object of interest. We have to be careful because it says what is the tension in the string, which often makes us think maybe the string should be our object of interest. But recall, we usually want to make our object of interest the object that the string is pulling on, which in this case is the ball. So the ball is our object of interest. What forces are acting on the ball? Let's draw our free body diagram. Well, we certainly have weight down, and we have a buoyant force upward because it is immersed in a fluid. We also have a tension force, and in this case, the tension force is pulling down. There's our free body diagram. No reason at all to do anything goofy with the coordinate system, standard coordinate system. Moving on, the next step in our force problem-solving strategy is to apply Newton's second law. In this case, we only have one dimension to worry about. So we're going to apply Newton's second law in the vertical dimension. We have the sum of the forces in the y direction equals 0. It equals 0 because it's not accelerating. Recall that this means that it is in static equilibrium. Our next line should be writing down what these forces are. We have a buoyant force. It's pointing up, so it is a positive buoyant force. We also have tension and weight. Tension and weight are both pointing down, so they should both be negative. Now we have applied Newton's second law to this situation. Next we should reassess and see where we're at, see what we're looking for, and see if we've got what we need here. We're looking for the tension in the string. Well, good news is it shows up right here. We can isolate tension like this. Buoyant force minus the weight. Here are my two blocks. This is my wood and this is my styrofoam. Let's say that the styrofoam has a density that is 1/3 the density of the wood. These blocks are the same size. How do their weights compare? Well, if the blocks are the same size and the density of the styrofoam is 1/3 the density of the wood, then the weight of the styrofoam is 1/3 the weight of the wood. The buoyant force is equal to the weight of the displaced fluid. So this is going to be the density of the displaced fluid times the volume of the displaced fluid times G minus the weight of the ball. Let's look at this term right here. The density of the fluid is 3 times the density of the ball. How do the volumes compare? How is the volume of the displaced fluid compared to the volume of the ball? Hopefully, you said in your mind that they are the same. right? The displaced fluid, the volume of the displaced fluid is equal to the volume of the ball because the ball is completely submerged. In other words, how much water is not there? What is the volume of water that is not there because the ball is there? Well, it's equal to the volume of the ball. So what we could do then is we could replace this. We could say the density of the fluid is 3 times the density of the object. The volume of the fluid is the same as the volume of the object. Density times volume is mass. Mass times gravity is weight. This is simply the weight of the object. This term right here is simply the weight of the object. Therefore, we have 3 times the weight of the object minus the weight of the object equals the tension. That is 2 times the weight of the object. The weight of the object is 1 Newton, and so we have that the buoyant force is equal to 2 newtons. We could have kind of jumped right to this step, couldn't we? Because the density of the water is 3 times the density of the ball, the weight of the displaced water is 3 times the weight of the ball. So, what can we conclude here? Buoyant force problems can be a little bit tricky, but at their heart, they're just force problems. And so as soon as you've decided that this problem involves the buoyant force, you're probably going to want to move straight to our strategy for solving force problems.